And I forgot to turn on my camera. I'm sorry about that. Okay, welcome back to chapter 10, I guess today. It's really going to be, again, it's building up on the stuff we discussed in the previous chapter. The idea behind this chapter is actually, I think, backward. It should have been before the previous chapter, because chapter 10 really talks about the work mainly of Mr. Kepler. I remember Mr. Kepler came way before Mr. Newton, about half a century before him, actually. And Newton was tasked really to explain or interpret the work of Mr. Kepler. By the way, what the simulation behind me here involves 4 or 5 planets in here. I mean, 4 outer planets plus the hypothetical 5th planet. I put them next to one another, and they all collided with Jupiter because Jupiter is so massive, including the 9th planet that I added there to the mix. Okay, and so it's actually coming from that software I was showing you earlier. Anyway, so the work of Mr. Kepler really should have gone before. Chapter 10 really should happen before chapter 9. Historically, that's how it happened. And actually, conceptually, probably it should have happened that way. And in other textbooks, that's how usually it happens. We go through Kepler's laws, and basically after that, we go into Newton's basically interpretation. But in this textbook especially, it happened in this order. I think my computer is lagging a little, so I'm going to stop that software. I was going to show you basically how the Kepler laws would work, but hopefully with just enough basically graphics from the software itself, from actually the PowerPoint. Hopefully you'll understand how that is. Okay. Anyway, so let's get into the PowerPoint, unless you guys have any question for me. Share. Where is it? Okay. Where is that thing there? And I lost the show more. There, chapter 10. So like I said, since Kepler's really observations were way before Mr. Newton, it took him a long time, Mr. Kepler, to come up with his 3 laws. And they're actually based on the observation of Tycho Brahe, the one who hired him, and he was his assistant actually. And after Tycho Brahe, he was really safeguarding all of his observations. And after Tycho Brahe passed away, then Mr. Kepler took those observations and basically started analyzing them, and he came up with 3 laws. So if you guys don't mind, this is actually what I'm going to start with. I'm going to start this chapter from the section that deals with Kepler's laws, because really they're the foundation, they're the target where we're supposed to be headed, okay? Then in order to understand Kepler's laws, or at least what they are talking about, in order to basically visualize the orbits basically of different objects around stellar objects, we have to go then to the projectile motion, because the projectile motion is actually, it's trying to put an object into orbit, even the one that we did in lab. So when you throw a rock, if you throw it fast enough, it could go into orbit. But unfortunately, on a day-to-day experience, we don't achieve those speeds. But if we do, then it's going to get into orbit. Projectile motion turned out to be a 2-dimensional motion, which is similar to what's happening for the planets. Actually, the planets, all of them, they orbit the sun on the same plane. Okay. Before Mr. Kepler, before Tycho Brahe, there was Copernicus, and before Copernicus, there were other people who theorized that the Earth must be the center of the universe. Copernicus, when he came in, he said, no, that's not correct. It is actually the Earth and everybody else revolving around the sun. And that was a major revolution. He was basically asked by the church to fix the calendar, because in the calendar that was relying on the calculation about 2,000 years before, or at least 1,500 years before, they were giving, it shifted so much that Christmas was not happening and where it's supposed to be, and Easter was not happening when it's supposed to be, and so on and so forth. So the church actually commissioned Copernicus to fix that. In doing so, he ended up basically noting that it's actually the Earth is not the center of the solar system. And that was a big problem, because he himself also struggled with that. And he did not really want to publish that work because there was a problem and he couldn't explain it himself. And that at that time, with his work, because if the Earth, for example, and I think we talked about this one a long time ago, if the Earth really were moving, how come a bird sitting on a tree would come down and catch the worm? Because by the time it tries to fly from the tree, the Earth and the worm would have moved away, moving around the sun, and the bird basically will be left hanging in the air by itself. So that was an issue that he struggled with personally. He couldn't really reconcile that idea. It took the work of Mr. Galileo later on, based on his observation of the inertia, that look, both the Earth and the bird and the worm, they will all drift in the same velocity with respect to the sun, and the worm still catches the bird. So that fixed that issue with Mr. Kepler's observations. There was another problem that Mr. Kepler actually, Mr. Copernicus really postulated, and that was the planets revolve around the sun in circular paths. That was in the belief that the heavens must be perfect, and all the heavenly objects, the planets, the moon, all the objects, they're living in heaven and heavenly, basically in the heavens. Therefore, their orbits cannot be nothing but circular paths, and the circle is known to be the most ideal shape there is. So that was the belief that was there. But of course, when Mr. Kepler was looking at those observations, let me straight jump into that slide, okay? Because we're talking about Kepler's laws, really. And this is the target of today's topic anyway. This is where we're supposed to be getting at. If I can find where his laws are. So the first law of Mr. Kepler basically states that the orbit of the planets is not a circle. Okay, it's actually an ellipse. An ellipse is more like a shape that this form. It's characterized by two focal points, and the distance from every point on the ellipse to those two focal points is the same. The sum of these two distances, this one plus this one, it's the same distance regardless of where you are. If you are there or here, so this distance to this focal point with this point is going to be always the fixed. So that's the definition of what the ellipse is. So that's one thing. And that was a problem because that really went against the belief of everybody that the heavens are perfect. So that was an issue for Mr. Kepler that he had to overcome. The second law, basically, if you take a line where the sun, basically, the first law says the sun sits in one of the focal points, either this one, if you like, or if it's not on that one, it's on the second focal point, end of the story, one of them, okay? The other one is empty, there is nothing in it, okay? So, the second law says, if you take a line and you draw it from where the sun is to any planet, and at that time there were only basically the planets that were known were Mercury, Venus, excuse me, Mars, and of course Earth. Now we know that Earth was, okay, is a planet too. Mars and Earth, Jupiter and Saturn, okay? 6 planets that we know of. Okay, the Earth is really, we're living on it. So in addition to this 5 plus 1, if you want to call it planets, because with the Earth we're living on it. So the 5 objects that we see in the sky, they're basically Mercury, Venus, Mars, Jupiter, and Saturn. Plus, we see also the moon moving around the Earth too, and we see the sun. That's how we ended up actually with 7 days in the week. We ended up with sun, the day of the sun, Sunday, the day of the moon, Monday, the day of what is it, Tuesday, which is the day of Mars. In French, it's mardi. I think there is a word similar to it in Spanish too. We ended up with a day for Mercury, which is Wednesday. We ended up with a day for Jupiter, which is Thursday. We ended up with a day for Friday, which is actually Venus. And we ended up with a day for Saturday for Saturn. So that's how we ended up with 7 days. At that time, we didn't discover Uranus yet, and neither Neptune. Uranus was discovered by accident, actually. And then Neptune was discovered by calculations. If we knew about the other 2 planets, then the week probably will be more, okay? Would end up with 9 days a week, okay? So that's one of the things that we know of. So if we take any of these planets, it doesn't matter which, even the ones that we discovered later, and draw a line from the sun to either of these planets and wait a given amount of time. Let's say, for example, 1 week. the planet will move from B to A or A to B. Let's take it from A to B. Let's say, for example, it was at A, then it will have moved to B. It's a small distance, isn't it? So it will sweep this area, okay? I calculate the area, I find how many meters squared there is, okay? Then, in the same amount of week, if I take any other location, for example, in C, and wait for it to travel to D, okay? Here. It travels a bigger arc, and the area here, this area and that area are the same. The arc is bigger, but the distance is closer. The radius is closer, actually. The arc of the radius of the curvature is smaller, and the areas are equal. That was the second law that he also discovered, which was actually kind of quick. Both of them he discovered quickly. The third law took him a long time to find, and basically the third law was that the time it takes for a planet to leave any point, okay? Let's take it counterclockwise, the normal positive direction. And it's going to go from A back to A, any point, from D back to D. That is a year on Earth. Today is September 24th of the year 2020. If we come back September 24th of the year 2021, 1 year would have passed on Earth, okay? It's more or less depending on the other planets. For example, Mercury and Venus have their period is less than that of the Earth. Any other object outside of the Earth, their period, their year is longer than that of the Earth. So that's one thing. If I take this period and square it, okay? If I take the average distance from the Earth to the Sun, or from any planet to the Sun, the average distance, and cube it, power 3. The ratio of these two numbers is fixed. It doesn't change. That took him a little bit of time to figure out, but that's basically the 3 laws of Kepler. That's what actually Mr. Newton ended up explaining based on his law of gravity, the universal force and all of that. He was able to explain the paths basically by solving the conservation of angular momentum, that all the paths, first of all, they are in the same plane. That's the conservation of angular momentum. And the conservation of angular momentum requires that these paths actually are, they sweep equal areas with equal distances. And the solution ends up to be one of the conic shapes. All of his equations, they give you one of the conic shapes. Either the path is elliptical, like all of the planets do, or actually circular, which is actually another solution that goes beyond what Mr. Kepler had observed. It could be circular, but for that, you have to have the speed constant. The planets do not have speed constant. So if there is an outer body out there that has a fixed speed, that body will have a circular path, okay? So that's not out of the possibility. And actually the circle is a special case of the ellipse where the two focal points collapse on each other, because the circle is just an ellipse with a single point, basically, which is its center, okay? And then there are two kinds of possibilities where the orbiting object will orbit only probably once and will never show up again. And those are the so-called parabolic paths. That's also a solution to Mr. Newton's equations, and also hyperbolic path. But those two, they are characterized with an energy that is big for the object not to stay in orbit. Basically, it's going to escape the gravity and go outside of that, the attraction of that object. So Mr. Kepler explained these laws, and not only that, but he found that ratio, the ratio of the period squared over the distance cubed, okay? So that's basically what we're talking about in here, in connection between chapter 9 and chapter 10, how these two chapters are related to one another. So now Mr. Kepler did this observation based on the data of Mr. Tycho Brahe, and based on that, he came up with these 3 laws. Mr. Newton, using his own laws of mechanics that he has developed later, he was able to explain all of these 3 laws and go a step beyond and explain other things. For example, the path of Halley's Comet, which is extremely eccentric path. how flat, because now some of the ellipses, they are flatter than others, is called the eccentricity. So how eccentric the path is depends really. I mean, some objects are more eccentric than others. For example, the Earth, its path is almost circular. As a matter of fact, we go between slightly more than 150 million kilometers away from the sun to slightly less than 150 million kilometers away from the sun. But for example, if you take the Halley's Comet, it has this orbit where the sun at some time is going super fast. It heats up, and when it heats up, it gets a tail, and that's what we see. Then when it moves away around just the distance from here to Jupiter, then at that point it freezes again and becomes solid ice, and then spends most of its time away from the sun. This whole motion takes about 76 years. So that's basically what we observed. So this was explained by Newton's laws of motion. It was not part of Kepler's observations or Tycho Brahe's observations. It was Mr. Newton who was able to explain Halley's Comet and any other object after that. So, having enticed you enough, hopefully, to understand the big thing, which is the solar system, let's go back into the topics, namely the projectile motion. Fast-moving projectiles, that's basically when they become satellites. So if you throw a rock fast enough, it can become a satellite. It's never going to fall, because as it's falling, it's actually catching itself, basically, continuing in the direction where it's falling. So it's trying to fall, but it catches itself. Circular or satellite orbits, that's a possibility, actually. Like I said, it's one of the solutions of Newton's equations. Then elliptical paths is exactly what we're talking about in here for the planets. And we talk about the conservation of energy. It turns out to play a major role in determining what kind of path a satellite will take. Okay, it's the total energy. So if the kinetic energy is higher than the potential energy, in this case, the object can escape gravity. When it's closer from the sun, it has a very high kinetic energy. It's moving super fast, and it's very low potential energy because it's close. Remember, it's 1 over r squared, okay? I'm sorry, 1 over r, the energy, okay? Since it's very close, and it's a negative number, actually, okay? Since it's close from the sun, its magnitude is actually, how should I call it? Higher in magnitude, but since it's a negative number, it's a lower actually potential energy. When it's very far away, this magnitude is actually very small in magnitude, which means it's bigger in terms as a negative number. So it's a sign issue now here, okay? Then we'll talk about the escape velocity and try to understand what Mr. Matt Damon did trying to escape Mars in that movie. But the point in here is that that's actually related to all the objects that you would want to put out of orbit, including objects that you would want to send them out of the solar system. They really need to have an escape velocity from the sun, okay? So this is a true statement for every object. There is an object that its escape velocity, there is no escape velocity for it no matter how fast you go, and that is actually the black hole that we discussed last time. The black hole, it's characterized by something called the event horizon, and the event horizon can be calculated when the escape velocity is equal to the speed of light. That means if you pass that line, even light itself cannot escape. You have to be moving with the speed of light to escape, and you cannot, let alone light itself cannot. So if you pass this line, that's it. That's a line of no return in terms of black holes, okay? Fortunately, for all of the objects that we deal with on a daily basis, like the Earth and the Moon and the stars, and the stars, including the sun and all of that, they're much, much smaller than black holes, so they have a finite escape velocities. So if you have enough money, you can build a powerful enough ship to escape basically the planet and go somewhere else, okay, including the star and so on and so forth. So without gravity, a tossed ball, this is something that you guys, the ones who are sitting in physics 11, they already are experimenting with, and they have a lot of data and they know what's going on in here, more so than the people probably who are sitting in physics 10 by itself, because I have had a big lab on it and it's still due on Friday, so they're still working on it, okay? And basically without gravity, a tossed ball object follows straight line. So if there was no gravity in this case, there is no force, so ball will keep on going, but with gravity, it's going to drag it down. And the motion usually is two-dimensional motion, like as I said before. In the x direction, if we neglect air and we neglect air resistance, we neglect everything, it's a uniform motion. That means the distance between this point and this point, provided that you're taking pictures at fixed amount of time, basically the time separation is the same, these distances are the same, okay? The distance between these marbles at different instances. Whereas if you take the picture in the same time, again, let's say for example, every second I'm gonna take a picture, this distance is not as much as distance, which is a lot smaller, and this one is even bigger than that one, which is bigger than the first one, and this one is bigger than all of them, and the distance starts to increase. So that's what an accelerated motion is. So vertically, it's accelerated by an amount of g. Horizontally, it's uniform. Horizontally, it's uniform. There is no acceleration. V is constant. Whereas V in here is increasing. V is actually increasing with g times t. The longer you wait, the more velocity you gain. Meaning every second, you're going to get 10 meters per second for every second, okay? 10 meters per second, really, okay? 9.8 if you really want to be more precise about it. Again, if you throw a projectile, it's going to follow a parabolic path, actually, parabola. That's what the shape is of this thing in here. If you're sitting in here, of course, and you were not paying attention, you would think that this thing fell on your head straight out. And it fell really following the law of 1/2 of gt squared, okay? So straight out. So this distance should be as if the distance with which it has fell in the same amount that it has traveled, at least vertically, okay? Again, different initial velocities will yield, again, this is the motion, the horizontal motion. This is the vertical motion. The horizontal motion is uniform. The vertical motion is accelerated. The combined motion, you're moving uniformly while you're accelerated downward, okay? So this is the actual path. Okay, this is the actual path. Okay, so that's basically how the parabolic path is. The velocity has two components, an x component and a y component. That's the initial velocity. This is the thrust. This is how much you push the object. This is when you kick the ball. This is how much you kick it with. So that's the initial velocity. Give it a momentum. So divide the momentum by the mass and you will find the velocity. So this is the initial velocity. It has an x component, v naught x, and it has a component in the y direction, v naught y. At any time later on, v naught x is the same. It never changes. The velocity in the x direction never changes because it's uniform. Whereas in the x direction, in the y direction, the vertical direction, it starts big and starts to be smaller and smaller until it vanishes. At this point, you have reached the maximum height. So this height is the maximum height, h, okay? The time it takes you to go to the maximum height is what we call the time up. This is the time for you to fly upward, okay, to your maximum height. Then the velocity changes direction. It was going up, now it's coming down in the y direction. In the x direction, it stays the same. So the x direction now is pointing down until it's going to be equal to this velocity, but opposite when it lands, okay? Provided it leaves the plane and comes back on the same plane, okay? It doesn't really fall on the other side. If you throw it this way, on a cliff, for example, it's going to land with a different velocity than it left with in here, okay? So this velocity will be higher. But if it's the same plane, the velocity should be the same, okay? So that's one thing about the projectile motion. This time from here to here is the so-called time of flight, time while it's airborne, okay? Usually, it's equal to twice the time it went up, okay? The distance from here to here, the distance from the beginning to the end on the horizontal plane is what we call the range, okay? So this is the range of the projectile motion. There is a beautiful mathematics to go with it. Basically, if we're doing the math for this one, and I think the book has a lot of formulas for you guys. You need to probably review them because some of the problems will be later on dependent on them. So the T up is when this velocity cancels. Remember, I have an angle in here, theta. That's my initial angle, okay, with which I threw. So this one has to do with V naught times sine of theta. So that's when the component in the y direction divided by G. So that's the time up, okay? Twice this much gives me the time of flight. The range now is related to the expression that has to do with the x displacement. So the range in this case is given by V naught squared times, what is it, sine of 2 theta divided by G. Again, these expressions are needed for some of your calculations. The derivations involve a little bit of calculus or some stuff like that, but it doesn't really, sometimes you don't even need calculus, I'm sorry. You can do just a little bit of algebra and trig, but since you guys probably are not required to do trig, here are the formulas for you to find all of this information about it, okay? So some of the applications will have this stuff in it. You should be able to get sine of 2 theta and sine of theta and things like that. If not, I will provide the information for you guys, okay? But V naught squared and all of this should be easy to do. So this is in a nutshell what the projectile motion is. It's characterized by an initial velocity, the angle with which you throw the project. It's critical, the angle, okay? And then from there, you can find the time of flight, you can find the highest point it reaches, you can find the range, you can find everything, okay? Again, this is the first example I was talking about, and here it's different. Of course, you throw it from an initial height, okay? So it's going to follow downward motion. Again, the way you're falling in here follows this law, which is 1/2 times G times T squared. And 1/2 of G is 10, so it's 5T squared, okay? Unless otherwise told, use the value of G to be 10, okay? I know in the lab, we were picky about this one because the lab, you would want to be precise, okay? And homework and other problems, you probably want to just get a rough number in here, okay? That's why G equal to 10 is good enough. 9.8, the difference between 9.8 and 10 is what, 0.2, which is 2% error. So that's acceptable, but in a lab, you would want to get as much correct values as possible. So 1/2 of 10 is 5. That's where this number 5 is coming from. Again, I was talking about this velocity and how it breaks down. And here is something that was also part of the lab, and that is the complementary angles will have the same range regardless. So I have 15 degrees and 75 degrees. That is, they add up to 90 degrees. They are complementary angles. So the range of the 15 degrees is here. The range of the 75 degrees is also here. Whereas the 75 degrees will have a much higher height than that of the 15 degrees and will require initially a much higher velocity. I'm sorry, the velocity is the same. What am I talking? That's nonsense, okay? But at the end of the day, the time of flight will be much higher than this one because it stays longer in the sky, okay? It goes with a lot of hoopla, but at the end, it ends up in the same points. The 30-degree angle, 30 plus 60 is also complementary. The 30-degree angle is here, and the 60-degree angle is in here. Now, the 45-degree, and that's one of the questions that you guys ended up having in lab, for those who are doing the lab, has that first question actually was that peculiarity of the 45 degrees, and I know I gave you an answer here and there, and that would work too. But here is another argument for it. 45 degrees is actually its own complementary, okay? So that's really the only one that stands out. That is where the maximum range will be. This is the maximum range. So if you're gonna be somewhere where you're shooting targets or something and you would want to hit the furthest point, 45 degrees is your best, provided there is no air resistance, okay? Now with the air resistance, this number drops. In the case, for example, of baseball, it can drop to 25 to 34 degrees. So if you are what is it, a batter, you would want to reach that range, okay? You would want to do this too to get a home run. In golf, it's actually higher, okay? So depending on the size of the ball, the shape of it, and again, also the conditions that you have in there. Again, I was talking about the speed being the same 40 meters per 40 meters, as long as you are on the same level. As long as you are on the same level, always the velocity is the same on the same level. Here is the only point that is its own point. That is the maximum. Okay, the velocity of a typical projectile can be represented by a horizontal and vertical component. So you have vertical motion and horizontal motion. Assuming negligible air resistance, the horizontal component along the path of the projectile never changes because there are no forces on the horizontal plane, because we're assuming there is no air resistance. There is actually a variation of that lab that I've been referring to for physics 11, where they actually include air resistance at the end. So when no air resistance acts on a fast-moving baseball, its acceleration is always downward. That's the only acceleration that you have. So the baseball is going like this. It's at any point, it's accelerating toward the Earth by the same amount, 10 meters per even when it left and when it lands, okay? It's always 10 meters per second, or 10 meters per second squared, or 32 feet per second, whichever way you like. So neglecting air drag, a ball tossed at an angle of 30 degrees with a horizontal will go as far downrange as one that is tossed at the same speed at an angle of, which angle adds up to 90 degrees when I add it to 30 degrees?
60.
So that's the one, okay? So that is the one, because those are the complementary angles. 30. So if the question was, let's say, for example, 17, which angle would be? None of this. Somebody wrote the answer already? 73, that's correct. I need to find the one, so that when I add it to this guy, they should give me 90 degrees. So if I send it 17 degrees, which is like this, I have to send it like this at 73 degrees to end up with the same range. This is not the question of the day, though. Still have some other questions, okay, coming. Satellite motion is an example of a high-speed projectile. That's one thing. So basically, as I said before, this is really setting you up for the satellites. A satellite is simply a projectile that falls around Earth rather than it into it. So a satellite, here is the Earth. It really wants to fall. I mean, ultimately, if it has a lower enough velocity, it's going to fall here. But it's going to end up in here if it has a higher velocity. It's going to end up in here, which even have a higher velocity than the first two cases. And it's going to fall almost here if it has even bigger velocity than the previous cases. But it's going to fall back into where it was. Basically, it catches itself before it falls. So it's always falling, but not toward the Earth, falling back to where it was started from. And that's good. That's basically what satellite is. So it's a projectile motion, no more. Except for landing on some range. So the range in this case is, there is no range. Okay, it's a range, it's everywhere. So that's the only difference with it. It moves so fast that it does that to you. That's exactly what the moon is. That's how Mr. Newton made his argument, that actually the moon is actually falling toward the Earth, but it's catching itself. It's doing exactly what we're talking about. So the moon is a satellite of the Earth. And so are all of the 70 moons or so of Jupiter. They're satellites of Jupiter. And in a sense, all the planets are satellites of the sun. So if you want to think about it this way, they're all catching themselves before they fall. So that's exactly what they are. So they are all projectiles. Okay? They have high enough velocities so that they come back into their orbit. If they move too fast, though, if they move faster than this speed, This is where they're going to end up. They're going to spiral out. So now they're going to move out. Next time they come in, they're not going to be in the same place. The next time that they come in, they're going to, so that's how they basically leave the planet. So if you would want to, if you are on a certain orbit and you would want to go higher, you probably need to accelerate. Next time around, you're going to go higher. You're going to move faster. Sorry, yeah, what am I saying in here? Yeah, you're going to get on a higher orbit. Does this make sense? Yeah, okay. So you gain more kinetic energy that way. I think I probably have it backward, don't I? I really need to think about this one. Don't quote me on it, okay? Okay, here is the example. As the ball of the girl, it always drops 5 meters per second. For the first second, I'm sorry. The first second, 5 meters. Depending on its initial speed, though, if she throws it with a lower enough speed, it could end up on the ground. But if she throws it with a higher speed, the 5 meters it falls short below the ground. So it could end up somewhere else. So it's going to require more than a second to land. If she throws up with a higher speed further, it's probably going to require even more, maybe 2 seconds before it lands, or 3 seconds, or 5 seconds, or no matter what that is, going to stay in orbit. Okay. I need to think about that question because I think now. Yeah, if it slows down, it's going to come back. If it slows down, it's going to come back. So that's correct. Okay. So if you would want to go higher in orbit, you have to move faster. Again, this is the example. So if you're doing this, this is what the boomerang is from the Australian culture, okay? So this is how it works, I guess. Okay, they throw it fast enough so that it lands on the other side, the opposite side, comes back to you. Or I guess it goes like this. It doesn't go around the Earth. Anyway, if you do that, make sure that you duck, okay? Otherwise, it's not good. So where we put the satellites, usually we try to put them outside of the atmosphere. There is air resistance, and usually they lose energy, and that's that sometimes they will be decommissioned and basically taken out. And the orbit's usually around 200 kilometers, okay? That's what the ISS is right now. Those are not the so-called geocentric orbit satellites, the one that I use for telecommunications. Those they sit at a much higher altitudes because they require each 24 hours to be in the same to move around the Earth once. Okay, that means they spin as fast as the Earth spins around itself. So as far as we're concerned, they're always in the same point in the sky. Those they need to be further away. They need to be in the 35,000 kilometers or more away from the surface of the Earth. Those are used for telecommunications, for GPS, and for other things. Okay, this one is just for other purposes. So these are low orbit satellites. So the motion is perpendicular to the force of gravity, and the period of the satellite for satellites closer to the Earth, they have a short period. For satellites further away, they have longer periods. For example, for satellites of 90 minutes, that means they're very short from the Earth. Every 90 minutes, they go around the Earth. For example, the satellites, as I mentioned earlier, the geocentric satellites used for GPS, their orbits much higher, and their period's about 24 hours. They have to be 24 hours. They have to be exactly 24 hours. As a matter of fact, they have to be to the second with the rotation of the Earth, which is slightly different than that of 24 hours. And they are so precise that they have to actually be running, not using classical mechanics, but Mr. Einstein's mechanics. Again, this is basically the curvature of the Earth. It drops for every 8,000 meters, 8 kilometers. That's about 5 miles, 5 meters. Okay. So if you're going to do this experiment and prove those people who talk nonsense that the Earth is flat, and you show them that the Earth is not flat, don't take binoculars and put a 5-meter stick and say, okay, I can see the stick now. That doesn't make sense. I mean, I'm not supposed to see. I'm supposed to see the horizon. Take a laser beam, okay, and shoot it, and you should tip the end of the 5 meters, okay? If you put it on the ground. If you put it above the ground, but let's say 1 meter, this one has to be actually 1 meter high too, above to the 5 meters, so it should be 6 meters. And then it should also hit it right in there, and the experiment should work, okay? So if we want to put an object into orbit, we have to do that. We have to make sure that at least for every 8 kilometers is going to drop basically by this 5 meters to stay in the same level. So if that girl wants to throw a rock from right the ground and have it come back on the ground, orbiting the Earth, hopefully not hitting any building or any dogs in the way, then that's what she should do, okay? 8 kilometers per, so that it falls 1 meter. Remember, it falls after 1 second, it's going to fall 5 meters, okay? So 8 kilometers per second should put it right in orbit. That's fast, that's super fast, okay? 8,000 meters per second, I don't know how many miles that is. It's going to be very, very big, super fast object. So when you toss a projectile sideways, it curves as it falls, okay? Because the Earth spins, actually, regardless. What will be in Earth orbit if the curves matches that of the Earth? So that's basically what we're saying in here. When a satellite travels at a constant speed, this is the only case when the path is circular path, okay? If it does not travel with constant speed, the path is not circular. So again, a rocket is thrown up usually when it gets above the atmosphere or around where it wants to be in orbit. They redirect it and then it starts to spin and it goes into a direction in that. And this is the speed with which you need. 8 kilometers per second, so that it drops after the first second 5 seconds, and that 5 seconds will catch itself up so that it stays in the same horizon, same level basically. It stays in that orbit. Here is your task for the day today. This is different though. This is not like what we've been doing before. You can Google this. If you're still having difficulty with it, please let me know how to build an ellipse. Let me explain how that works. You need a string. I have this one about 20 centimeters. This distance from here to here is 10 centimeters. So originally it was about 20 centimeters, okay? Anywhere between 18 to 24, 25 centimeters is good enough string. You tie it from one end, okay? And you get some thumb tucks with those things there that you want them there. And you nail them, you put them on a piece of paper, and be careful not to poke yourself, first of all, and probably also the surface beneath it. So probably what you could do in here is put a cardboard underneath. Any cardboard will do, so that you put the piece of paper, a white piece of paper, the one that you would want to draw the object on, and separated by about 5 to maybe 7 centimeters, okay? 8 centimeters at most. Don't make it too tight, okay? Make them 5 centimeters would work, 6 centimeters would work. Any number you choose is fine, okay? Don't make them too close that it becomes like a circle. Don't make them too wide, which is going to be very hard for you to get the tension in here. So make it about 5 to 6, 7 centimeters, whichever is easy for you. Then take a marker or a pencil and push it against the paper now that it's fixed from the other end, and move the basically the pen around, drawing your own elliptical path. Okay, you guys understand what the task is? So task is number 1, There are several components on it. Hold on, okay? Number one, draw an ellipse. Okay? Number two, measure this distance from where it's bulky, from where it's basically extends the furthest. So I'm going to call this distance the distance big A. So measure A. Okay. Now I'm going to draw with a different pencil. From when it's thinnest, measure this distance now only from here to here. Okay. And call that distance B. Okay. Now, fourth thing to do is to measure the distance between thumbtack and thumbtack to where you nail this distance in here. And call it C. Okay. What I need from you are the following. I need A, I need B, and I need C. As a bonus, if you like, you can include the picture also. You don't have to, but it would be nice to include it. Okay. There will be a follow-up to this one, which is part of your assignment too, actually. Immediately after you get A, B, and C, you're going to pick up somebody else, A, B, and C, and do a formula. I'm going to tell you what that formula is. Okay. And to tell them how off they were, if they did a good job or not. Does everybody understand the task or not? Okay, Arturo, Isaac, Joshua, everybody. So the first thing is get thumbtacks, 2 of them. Not now. Kyle, not now, okay, after class, okay? Get the 2 thumbtacks, get the string, okay, string, about 20 centimeters long, okay? It doesn't have to be exactly 20. Tie it from one end, right? Put the thumbtacks on a piece of paper, white piece of paper, and to make sure you don't harm yourself, because those are sharp things, okay? Put a cardboard underneath, okay? And then about 5 centimeters away from each other. They could be 6, they could be 7, it doesn't matter. They could be 5.5 or we care. But as long as they are not on top of each other, they are not 2 centimeters or 1 centimeter apart, okay? They are not actually 10 centimeters apart, because that's going to be very hard for you to do anything with. Then draw your ellipse, that's the first task. Then take from the further to the furthest, measure that distance. From the smallest to the smallest and measure that distance. The first distance is A, the second distance is capital B, and then the distance between the thumbtacks themselves, okay? Remember I told you about 5 centimeters apart or 6 centimeters apart, so it was 5.5, mark it as 5.5. I need how much is from end to end. I need also how much is from small to small, and I need also the distance between your thumbtacks. If you include the pictures, that's fine, that's good actually. And later on, you're going to pick somebody else. I'm going to post the formula to use, basically, and tell them how eccentric their ellipse is, okay? That's what we want to do, is find the eccentricity, how flattened those ellipses are, okay? Everybody is on board then. Very good. Very good. So let's continue then. Again, this is what I was talking about, the elliptical paths. It goes with a higher speed, and then it wants to escape, but then it comes back, it falls back, and then accelerates and comes back, and so on and so forth. So those are the speed of a satellite in elliptical speed. It's not constant. That was in the case of a circular path. Yes, it's constant. And here it's not. It's much faster near the focal point. By the way, where you put your thumbtacks, that is actually the focal points. Those are the focal points, okay? And if you ensure that the pen is always stretched right, okay, when you're drawing, that means the distance between this point and any point on the surface is the same from those 2 points. It never changes. Remember, don't tie it on the thumbtacks, okay? Make it loose, just put it around it, okay? Otherwise, you cannot go around it. You guys understand? That's important part of the process. So when very close, we're moving super fast. When very far away, we're moving very slow. So the answer to the question is not constant. The question is this one, A here. That is not part of the questions of the day, okay? Okay, Kepler, assistant of the famous Tycho Brahe, basically astronomer who directed the world's first observatory somewhere near the island. I forgot the name of it in Denmark. He's the one who did that. And he used to collect his data, and he found that motion of the planet was not circular, rather it was elliptical. So that's basically what Mr. Kepler has found. And those are the 3 laws we discussed already, okay? And now we have, since the kinetic energy has to do with the motion, how fast the object is, planets near the focal point, when they are close from the sun, they move faster than when they are away from the sun. But when they are away from the sun, they have a higher potential energy than when they are closer from it, okay? And here is the exchange. In a circular path, it doesn't change. It's always fixed number, okay? Potential plus kinetic, it's always the same. It never changes. But in a path that is elliptical path, the kinetic energy here is higher, and the potential energy is higher in this case, okay? So that's basically how we end up with this expression in here. So if the object has a very high kinetic energy to begin with, it might end up with a 0 potential energy at the end, meaning that the object reached infinity. It left, basically. It's never going to come back. Again, we're trying to use Kepler's laws now to understand the force of attraction, in this case, on the object. And the escape velocity is one of the things that we will need to escape the pull of any object. For example, this is Pioneer, one of the first satellites to leave Earth. On Earth, it's 11.2 kilometer per second. An object reached this speed will leave the pull of the Earth, basically. Will end up with a kinetic energy that is high enough so that it doesn't, the potential energy will be 0 toward infinity. So it's going to go forever, okay? For other planets, it's a lot less, okay? For Mars, it's a lot less than this one. For Jupiter, it's much higher than this number. So again, this is the objects that go out of the Earth to outside of the outskirts of the solar system to other objects in the solar system. You need to reach that speed. For the moon, it's a lot less. Why why when we went to the moon, basically the rockets that were in there, they did not require that much fuel to leave the moon, because they were dealing with much lower. Two things. First of all, the gravity there is a lot less, so the escape velocity is less. Second, they did not have to deal with the friction like in here on Earth, where the air resistance will slow them down. There, they don't have any air, so you don't worry about that. So that's really how. Any questions about this chapter and the task in hand? You have only one thing to do today. Don't you feel lucky today? Don't you think that you're lucky today? Yes? Okay, Jeffrey agrees. Okay, guys, I will see you, for those who are in Physics 11, in about an hour from now, okay? If you have any problems or this question about the tasks, please let me know, okay? I really don't want you to be stuck with it. This is a hands-on. I always like hands-on to do things. There are actually a lot of things to do. Can you say the 3 measurements? Okay, the measurements. Let me go back into something to show you how it looks like, okay? Let me grab a new slide in here, and let me go back into, so that you guys see exactly what I'm talking about in here. I don't want you to really be working in the dark in here. Okay, so this is a thumbtack. This is one of them. Oops. Okay. And this is another one. I need this distance. This we called it C, correct? Now I connect the string around it loosely, okay? And I take a pencil, I'm sorry, and tighten up, bring it tense a little bit, okay? I need to tense it, okay? I need to make sure it does not, so this is how it looks like. And run it around, okay? Then, if I do that, I take the ruler, and on this line, actually, measure this distance. That is going to be A. On the middle of where the C is, right in the middle, I draw the perpendicular to this line. That is where the B is. Do you guys understand the... Okay, no problem. Okay, do you guys understand now how it looks like? So those are the three measurements. I need A, B, and C. Yes, that's the question for the discussion today. So Kyle, is it good now? Okay, very good. So basically that's the entire task. If you include a picture of what you drew, that would be fine. That would be great. But if you do, I mean, that's fine. Don't do any more stuff with it, okay? It's all I need for right now. I'm going to give you the formula and the discussion. I tell you, take this one and use it against anybody else, not yours, okay? I don't want you to pick up yours and tell me this is the answer. This is my eccentricity. You go to, hey, so-and-so. This is, I think, what your eccentricity is. I think your ellipse is this flat or that flat, or it's almost a circle, okay? So that's basically how that the whole thing is. Got it? If you want to, you could take, I mean, it's going to be recorded, so you can come back to it if you like. Okay. Thank you, guys. See you in about an hour.